Okay, so now let's say a little bit more about exponential maps, and in particular exponential maps on matrix Lie groups. Okay. Okay, so if you have a matrix Lie group, right? So for a matrix Lie group, the exponential map is just given by the matrix exponential. Okay, so let's just call that EXPM. So, all right, and it's just defined to be, so given a matrix A, the matrix exponential is what you would expect if you were to look at the Taylor expansion for the exponential function, but interpreted all the operations in them in terms of matrices. So it's just the sum from let's say k equals to 0 to infinity of a to the k power divided by k factorial, with an understanding that a to the 0 is just the identity matrix. Okay. All right. And then you can check that in particular that this exponential m from a matrix Lie algebra to a matrix Lie group, right, maps the Lie algebra to the Lie group, as you might expect, right? Okay. All right. So you might ask, it's like, so the problem, of course, it's like with the matrix exponential is that it's not always easy to compute the matrix exponential for an arbitrary matrix. And it's because, in some sense, it's as easy or as difficult as solving all linear constant coefficient differential equations or systems of differential equations, right? Because, of course, the matrix exponential is related to the fundamental solution, it's like of the solution of a system of linear constant coefficient differential equations. Okay, so so you might ask the following reasonable question, which is to say, can you approximate the matrix exponential on the one hand, right? And of course, we can approximate it in the sense of the order of accuracy. It's like, if if A is sufficiently small, whatever that means, right? But then there's the other question of when you construct that approximation, does it retain this really, really nice thing, this property, it's like of the exponential map, which is that it maps the algebra to the Lie group, okay? So the point is that since the matrix exponential is difficult to compute in general, right, can we construct, it is natural to ask, if we can construct approximations of the matrix exponential that preserve the property that it maps the Lie algebra to the Lie group. Okay, so it turns out that for a special class of matrix Lie groups, there is a systematic way of doing this. Okay, so for what are called quadratic matrix Lie groups, so for quadratic matrix Lie groups, which basically means that you have some group G, which is a subgroup of the general linear group of n by n matrices with the property that G transpose JG equals to J for some suitable choice of J. Okay, so we say this is a quadratic matrix Lie group. Okay, and in particular, of course, it's like the rotation group. It's an example of a quadratic matrix Lie group. So if you're in this class of quadratic matrix Lie groups, right, then there's a natural family of approximations of the matrix exponential which preserve the property that they map the Lie algebra to the Lie group. Okay, so so for quadratic matrix Lie groups, the diagonal Padé approximants of the matrix exponential satisfy this property. Okay, so so the next natural question to ask is what exactly are these Padé approximants, and is there some sort of explicit expression for all the diagonal Padé approximants? Okay, all right, so let's just keep this part about quadratic matrix Lie groups for now. Okay, so the same way that you can have things like Taylor approximations, and you know, it's like, and so the Taylor polynomial, for example, is the, in some sense, the best, you know, it's like polynomial of up to a certain degree. It's like in terms of its approximation power, it's like of a given function. And so you can ask whether something similar happens when instead of looking at polynomials, you look at rational functions. Okay, and so the Padé approximant is an example of one of these kind of things. So the Padé approximant of the exponential, the matrix exponential, is a map, is, well, the unique sort of rational function, r hat, I'm going to write as alpha beta in rational functions with alpha degree in the numerator and beta degree in the denominator, such that, right, r hat alpha beta can be written as the quotient of a degree alpha polynomial and a degree beta polynomial, okay, with the property, and then there's some sort of normalization condition for the denominator. You want that the denominator evaluated at 0 is just 1, right? That's just a choice of normalization, if you will. And then you want p hat alpha beta to be in polynomials of degree alpha, and you want q hat alpha beta to be in polynomials of degree beta. Okay, so all that's saying so far is that you have it's like a rational function with alpha degree numerator, beta degree denominator with some normalization condition, and then you want it to be as high order an approximation as possible, and so what you want is that, and r hat alpha beta approximates the matrix exponential m, right, to order alpha plus beta, right, which is, as it turns out, the best you can hope for. Okay, so that's what this Padé approximant of the matrix exponential is. That's quite a reasonable object to look at. And you can actually compute, it's like explicitly what the numerator and denominator, it's like polynomials have to be. Okay, so the numerator and denominator are given explicitly by the following. Okay, so p hat alpha beta z is equal to the sum from k equals to 0 to infinity of alpha choose k. And then there's an alpha plus beta minus k whole thing factorial divided by alpha plus beta factorial. And then there's a z to the k here. All right. And then there's an expression for the denominator, which turns out to be related in some way to the expression for the numerator. So, so q hat alpha beta of z is going to turn out to be equal to p hat beta alpha of minus z. Okay, so basically what you do, of course, is that you use the expression it's like you have here, but you sort of replace alpha, you swap the roles of alpha and beta, and you put minus z instead. Okay, so all right, so this is the general form of the alpha beta Padilla approximant, and then if you recall, we were interested in the diagonal Padilla approximants because those are the ones which had this property that they mapped the Lie algebra of a quadratic matrix Lie group to that quadratic matrix Lie group. Okay, so that was a nice property which we would like to have. So in particular, right, for the diagonal Padilla approximants, what happens, of course, is that alpha is equal to beta. Okay, and you can write down what the p hat alpha alpha is. P hat alpha alpha of z is the sum from k equals to 0 to infinity. Okay, alpha k, right? So alpha and beta equal now, so that's just 2 alpha minus k factorial divided by 2 alpha factorial z to the k, and then q hat alpha alpha z is equal to p hat alpha alpha minus z. Okay, and then we can look at the lowest order case, right? The lowest order diagonal Padilla approximant is what is called the Cayley map. And it's given by this rational function. So r hat 1, 1 of z is 1 plus 1/2 z over 1 minus 1/2 z. Okay, so this is what is called the Cayley map. And the Cayley map is used very often as a approximation of the matrix exponential when you're doing numerical computations, for example, on the rotation group. All right, so let me just stop here for now.